Here we are today, and I want to talk about how we compute polar area. So because we're going to need a lot of writing here, I chose to just take a capture of some lecture notes I've had in the past, and I want to highlight things with all the text in front of us. Then, once we've gone and derived the formulas, I'll work an example problem or two. I also recommend Khan Academy has a nice video where he animates all this by hand and you can see him drawing as we go. So I highly recommend looking at that as well. Polar area, this is the first topic covered in section 10.4, where the idea is we have some curve, and it could look like anything that's starting to be drawn out on the polar axes. And to start out with, let's assume that the portion of the curve that's drawn initially, let's look at an r equals f of theta just for visualization's sake, where f of theta happens to be a function that's always positive. That's going to make life a little bit easier. So that we can imagine that as we're adding angles, as the angle measure increases, the curve is swept off in this positive direction, so that we're drawing out this portion of the curve moving around in the direction that I'm indicating here. So if we look at the illustrated image that I have on the notes, what we're going to consider is this curvy line. This is going to represent the graph of r equals f of theta. So this is some polar curve, like maybe it's a limacon or it's some sort of polar flower, any of those. Then we consider just how much area gets filled when we go between two particular theta measurements. And I've chosen here to have those theta measurements pretty close together in one quadrant, but every discussion we're going to have would not be dependent on them being this close together. All that needs to happen is that theta from alpha to beta would not repeat measurements on the curve. So we assume that we've covered a small enough measurement of theta angles that we are not repeating, we're not returning to any points. Theory is going to be, if I have some whole area range that I want to care about, we always use the word area swept out by a polar curve because of the fact that as we draw things in polar, they rotate out. They do this kind of movement. So if I want this area between these two rays, theta equals alpha and theta equals beta, so I'm really just looking at points that satisfy that with a positive radial measurement, then I'm going to play a similar game to when I was adding up areas in Cartesian, although when I add up areas in Cartesian coordinates, the tradition was we considered little rectangles moving along the axis. Well, when we look in polar, the analogy would be to consider teeny tiny wedges, little miniature sectors. I'll draw them in a few different colors. So these tiny little sectors, here's one. I'm going to highlight every other one a different color. Here's another. So I'm going to put all these tiny little sectors in. Let's put one in the middle. That's the third color. And we assume that these partitions and these theta values, the endpoints of each of these. So theta equals alpha, that's the theta 0. And then theta 1 is going to be the next ray measured, and then theta 2, so on and so forth. And so each one's giving us this skinny wedge. And just as in the rectangular case, like when we looked at rectangular coordinates, when we drew area like this, we said if we make that little rectangle measurement small enough, so if my slice is small enough, we're going to actually compute a little rectangle area. So we would use something like, maybe we're using the right-hand endpoint, and so we're really computing the area of the skinny rectangle here like this, and so we actually missed a little bit of the region. But the argument was as width of those little partitions went to 0, so if the width of the little rectangle was delta x, as that width went to 0, the limit of the sums of these little rectangles, where the height is given by, for instance, the value at the right endpoint, multiplied by this little delta x width, the limit of that as it went to infinity would in fact compute the entire area. Now, in order to compute little wedge areas, we just need to compute the area of a sector of a circle. So the formula for the area of a sector of a circle in general is if I have a circle and its radius is r, and I create a wedge out of that circle whose radian angle measure is theta, then that we'd want to know, well, what is the area of that portion? What is the area of this wedge? The formula for that is 1/2 r squared times alpha. The reason this is the right formula, I think, is always worth remembering. So the area of the entire circle would have been pi r squared. And whatever the measurement of alpha is some percentage of the entire circle measurement. So alpha, you think of alpha as what portion of 2 pi is it? So that if alpha were moving the entire way around the circle, we'd get a proportion of 1, because that would be 2 pi. But say alpha is a fraction of that, what fraction of the total circle's area would it be? Well, it's going to be alpha over 2 pi. That fraction times the area of the full circle. Now, if you multiply this through, you'll see the pi's cancel, and you get 1/2 r squared alpha. For that reason, the little areas that I'm adding up are going to be 1/2 r squared times delta theta, where delta theta is just the change in angle, the teeny tiny width of radian measure of this teeny tiny sector. How much angle measurement did we rotate out? If I add those all up, the value of the radius on each of these is going to be, so the r squared I'm going to use because it's a polar curve, that is f of some angle within there, so maybe it's the right-hand endpoint. But it's f of some theta j, where theta j is an angle in the jth partition of the interval, and that's what I've written right here. Okay. And so then we're just going to square those, and so I shorten the notation to r sub j for one of those. So I'm adding up 1/2 r sub j squared delta theta. When I create the Riemann sum of that, and I take the limit as n goes to infinity, so I'm adding this up over every single partition, then that is giving me an integral, a measurement from the lower alpha bound to the upper alpha bound of 1/2 my function for r squared d theta. And so we obtain the following theorem, or this is the statement of exactly what we're computing. For a continuous function f of theta, then the area bounded by the curve with polar form r equals f of theta, and the rays theta equals alpha and theta equals beta, so the area bounded by that curve in polar form, or swept out by it, if you will, is this integral 1/2 from alpha to beta f of theta squared d theta. Let's look at an example, sort of a proof of concept. Okay, so the basic example I'm going to use first is the curve where r is constant. It's always good to check those constant functions. So here r equals 2, so f of theta is the function 2. Now, we recall that is in fact a circle. So we've got radius 2. Let's just find the area swept out from theta equals 0 to theta equals pi. So notice that would be a half circle. We're talking about sweeping out and getting this area. So using the polar form, that's the integral from 0 to pi of 1/2, or f of theta, which is 2, so 2 squared d theta. So that's the integral from 0 to pi of 2 d theta, because 4 times a half is 2, and evaluating that would be 2 theta at bounds, or 2 pi minus 0, which is 2 pi. Notice that the area of the half circle would have been 1/2 times pi times the radius squared, and so we are confirming that we do get 1/2 times 4 pi, or 2 pi. So this is giving the right area for that curve. Let's consider it where the function that we need to deal with is a little more complicated. So let's look at this example. Find the area of the circle r equals 3 sine theta, which is swept out in the first quadrant. Recall that circle r equals 3 sine theta is going to have value 0 at the origin, and then its value sweeping out, the maximal value it'll have, when we put in pi over 2, we get 3 out. Oh, my art here is going to be hideous. But we're making a circle. Ugh. whose radius is 3/2, and remember the center would also be at 3/2. So that is a really bad circle, but there we go. If we want the area that's swept out in the first quadrant, we remind ourselves the first quadrant represents theta equals 0 all the way to theta equals pi over 2, so that my integral bounds are going to be 0 to pi over 2. 1/2, now I just need to put in r and square it. So 3 sine theta. Integrating that, I'm integrating 1/2 theta to pi times 9 sine squared theta d theta. So now I'm going to need to use a trig identity to continue this problem. So the one we're going to want is one of the identities that is the half angle identity. So recall, and these are worth memorizing, that sine squared of theta is equal to 1 minus cosine of 2 theta over 2. And for that reason, the integral that I want to compute is going to be rewritten as 0 to pi over 2, 9/2 times 1 minus cosine of 2 theta all over 2 d theta. I'm going to pull all my coefficients out front. 9/4 integral from 0 to pi over 2 of 1 minus cosine of 2 theta d theta. Okay? Let's integrate. We have a 9/4 out front. The integral of theta, or of 1, is just theta. The integral of minus cosine 2 theta would be minus 1/2 sine 2 theta. And then we're going to evaluate that at bounds from 0 to pi over 2. So we're going to get 9/4 times pi over 2 minus 1/2 times sine of pi over 2 times 2, so sine of pi. So that's going to have subtracted from it. That's all the evaluation at pi over 4. Then we'll have 9/4 times 0. But now it's going to be minus 1/2 sine of 0, which is also 0. And so we get as the answer here 9/4 times pi over 2 minus 0 plus 0, or 9 pi over 8. Now you may be saying to yourself, how do I know whether or not this answer is correct? Well, remember again, as I mentioned, we have this inclination about what circle we're talking about. The radius of this circle is 3/2, and we've been looking at the area of the part that's just in the first quadrant, swept out one time. So half of the area of a circle of radius 3/2. 1/2 of a circle of radius 3/2, so 1/2 pi times 3/2 squared. Well, that's 1/2 pi times 9/4, which is 9 pi over 8. So that's a nice check here that this worked.